So in this example, you constructed a confidence interval based on your past experience of people whose ages you knew and applying that to me. That's when we do this in class, when you do this in research surveys, you're not just going to guess a confidence interval, you're going to calculate it from a sample. You're going to take a sample from a population, calculate, you're going to estimate the population standard deviation, you're going to estimate the standard error, and you're going to use that to construct a confidence interval. So it's just based on the data. And I'll do that later too with with your survey as well. So in order to construct that confidence interval, you first need a point estimate. And remember that because the mean of the population and the mean of the sampling distribution are identical, the best guess, the point estimate, is going to be the mean of our sample. So you take your sample of n equals 30 or whatever, you calculate the mean, that's your point estimate. So it's your best guess. Even though you know it's not exactly correct, it's the closest guess you can make. So if I were doing that with the age survey, I would just take all of your point estimates and I would average them. And then we're going to use this central limit theorem and that part 2 that related the standard error to the standard deviation and calculate a margin of error. And I'll show you how to do that. So the margin of error is how big the confidence interval goes above and below the point estimate. So this is just an example of a 95% confidence interval. It's how far above and below 95% of the probability in the sampling distribution lies. So from the central limit theorem, you learned how to get the sampling distribution from the population distribution. So the middle of the sampling distribution is at x bar, the mean, and the standard deviation of it is the standard error. It's that sigma over square root of n. And all you have to do is a lookup in a z table for now, and to see how far above and below your point estimate you have to go to get 95% of the probability in your sampling distribution. That means that if you took an infinite number of samples, 95% of them would fall in this shaded area. Yes? You could use the empirical formula too. Yep. Yeah, you can use the empirical rule for the 95 or the 99 or the 60, the 66% confidence interval, or you can use a z table for other values. So you can do this, and as long as either n is larger than 30, so you have a large sample, or the population is normal and we know the standard deviation of the population. So that's a key distinction there, whether you're using the known true population standard deviation or whether you're estimating it from a sample. And when you have a small sample that you estimate the standard deviation from, that's when we're going to get into the t-distribution next class. But I didn't want to cloud your heads with additional concepts today. Just focus on the main concept of estimating an interval from a sample. So here is your basic formula for, or recipe for calculating a confidence interval. And I believe I've put on YouTube in the mini tutorials section a little section on how to calculate a confidence interval by hand. But you take your sample mean, and then for a 95% confidence interval, it's plus or minus 1.96 times the standard error. For 99%, it's 2.58. Does anyone know where you would get that from if you didn't get it from this slide? Where would that 2.58 come from? Yep, the Z table. So we would want the central area of the Z table that contains 99% of the probability. So if it's a left-tailed Z table, it would be the value of Z for 0.995, because it would be 0.005 of the probability in the right-hand tail alone. We could look that up right now. I think I have handy the textbook. Distribution tables. So I'm going to look it up under we can use the negative Z, it doesn't matter. We want a probability of 0.005 under the left tail, right? Because if we have 0.005 under the left tail, there will be 0.005 under the right tail, for a total of 0.01, which means 0.99 in the central part. So, see, I'll make this a little bigger. Okay, starting here, that's too small. Just gonna go down, 0.006. It's a little too big, let's go here. Oh, right there, so it's about minus 2.57 or minus 2.58. And what did we say on here? 2.58. Any questions about that? No, we're good. You don't need to think too much about the computational aspects of it. You'll do lots of that in the lab and in the assignments and preparing for the exam and everything. The main point now is that you understand what a confidence interval is and where it comes from. So this is the general idea that you take your, if alpha is 1 minus your confidence level, then you look up the Z value for alpha over 2 and multiply that by your standard error to get your margin of error. And it's the same thing whether we're talking about a continuous variable and the standard error of the means, or a binary variable with a standard error on the proportion. As long as you calculate the standard error, then it's the point estimate plus or minus the margin of error to get your confidence interval. Yeah. Oh, I was going to say, I sense I'm starting to confuse people. No. Okay. Alpha is 1 minus your confidence.
Oh, it's 1 minus.
Yeah. Yeah, so if your confidence level is 95% or 0.95, then alpha is 0.05. Alpha over 2 is 0.025. So you would look up the Z value for 0.025 unless you use the empirical rule, which is perfectly valid. Yes? The margin of error is half the size of the confidence interval. So it's the amount above and below the point estimate. The range is twice the margin of error. So the margin of error is half of the range. So the confidence interval goes from the point estimate plus the margin of error to the point estimate minus the margin of error. Yes. Let's see. Do I have is there a picture of that soon? Yeah. So in this, the point estimate is, so this would be the sampling distribution. The margin of error would be from the point estimate, which is a z value of 0, up to the positive limit, and also, which is the same as from the point estimate to the negative limit. So you could, on the scale of z, here on the 95% confidence interval, the margin of error is 1.96 in terms of z, and then when you multiply that by the standard error, it gives you your margin of error in terms of whatever it is you're actually measuring. Thank you. So some does and does nots of the confidence interval. Look carefully at this first one. It does not imply that 95% of the population values lie between these limits. So if we're talking about you know, the mean height of Hunter College students and we give a 95% confidence interval, does not imply that 95% of the students have a height in that range. Does that scream out at all of you of, oh my God, no, that's a horrible misinterpretation of the confidence interval? Because it should. It's only to do with our uncertainty in the mean. Nothing to do with the individuals or the proportion of individuals, right? It also does not account for bias in the point estimate. So it accounts for sampling variability, for the amount that average will vary from sample to sample. But if it's somehow biased because your professor has a young face, it doesn't account for that. But a couple things it does do, proper interpretations. It provides an interval in which we're 95% confident that the true value lies. That's a good interpretation. And also, if we were to take a large number of samples, 19 out of 20 of them would result in a correct confidence interval that contained the true mean. Let's see, Sarah has a question. I thought the z-score did imply that 95% of points were between those points. Okay, so we've been using, up until this point, we've been using the standard normal distribution and the z-scores for populations and for individuals. And for those problems, yes, a probability of 0.95 on the Z table implied that 95% of the population lied within that range. We're using it for something different now. So it's the same distribution, it's the normal distribution. This is a different application. So when you use it to calculate a confidence interval, it does not refer to the number of individuals in that range. Anyone want to say why? Yep. Right, the points on the distribution aren't individuals. It's the sampling distribution. And you remember it's different than the population distribution because it's standard error is the standard deviation divided by the square root of n. So it has to do with the distribution of a bunch of samples, not the distribution of a bunch of individuals. Does that answer your question, Sarah? So remember that this population mean, it's something that we assume is fixed and there's some true value for, but we don't know it. So like the age, there is a correct answer, but you don't know it. If we're talking about serum cholesterol levels and the average serum cholesterol for men in their 40s, there is some true value for that mean, but if you only get a small sample of individuals, you can only estimate it. So it's not a random variable. It doesn't have error. It doesn't have variance. It's just a single value. It's the answer. By the way, this is a frequentist. I don't know if any of you you probably haven't been exposed to enough statistics to hear about frequentist versus Bayesian interpretations, but this is a very frequentist interpretation, which is what I am for the most part. In your assumption, there is some true value, and you're trying to estimate it. And again, if we took repeated samples and constructed a 95% confidence interval around each one of those sample means, then 95% of those intervals would contain that true population mean, and 5% would not. They would be an erroneous confidence interval. Here's what that looks like. These are actually done by a simulation where I drew samples of a fixed size from a normal distribution with known mean and standard deviation, and constructed a confidence interval from each one of those, and put in red here the ones that did not contain the correct true mean. And it's about 5% of them, because these are 95% confidence intervals, about 5% of them failed to capture the true mean. All right, so I'm gonna keep on beating on this just and try and get see if we can get a few new people to answer questions here. So is the 99% confidence interval going to be larger, or is it going to be smaller than the 95% confidence interval? Larger. Yep. So as the size of the confidence interval increases, does the confidence increase or decrease? Confidence level. Yep, it increases. So the bigger the confidence interval, the more confidence you have in it. Yes?
Well, before you said the 50%, as it was bigger, the person was less confident.
Right, that's this kind of different meaning of confidence. Yeah, what I prefer to say is that person has less information about the true answer. Yes? Yeah, so as for a higher confidence, so in the first one, the higher confidence interval is larger, and then the second one is just asking the same question. If the confidence interval is larger, then your level of confidence in it is greater. And you can imagine that on this last one, these confidence intervals are all centered around the mean of around the mean of that sample. If we were to double the size of these intervals, there would be a lot fewer of them that failed to capture the population mean. So you'd be more confident that you're capturing the true mean. So the key thing here, if you're a betting person, it's in a way less important that you know precisely what the answer is, but that you're able to correctly estimate how confident you are in it. Because even if you don't have a lot of information, as long as you can give an interval where you know pretty well what the probability of being correct is in that interval, then you could place an accurate bet as long as you can find a sucker who is less good at estimating that than you. Poker face would help. What's that? Right, the payout is bigger when the interval is smaller because you have less chance of being right in the face of a fixed amount of knowledge. Yeah, if you're going to bet that in the Super Bowl there will be between 23 and 25 points scored, that's going to be a big payout if you're right. Whereas if you bet it'll be between 10 and 100 points, that's not going to be much payout. I'm not going to go through these in class, but you can. They're here for you to try out. In each of them, you'll have more of these to try. You're given a sample mean. Here's an n so that you can get the confidence or the standard error, and then you can convert that, the standard error, into a margin of error and calculate the confidence interval. All right, so let's wrap up this example. Here are the actual values, the guesses, with the plots. So I calculated from these. This is the mean of the point estimates. So the mean guess was 37. And this is how we would calculate a confidence interval using the methods that you're learning and that you're going to practice in your assignments in the lab. We can calculate a standard error. This is the standard deviation divided by square root of 6 of n, that's 1.1. Using this 0.67, this is not strictly correct. You should be using a t-distribution here, but we haven't learned it yet, so I just did it using z. It turns out for n equals 6, it'll be pretty different. I'll do it the other way next class, and you can see how different it is. But using that, I calculated the margin of error. So using the intervals that you gave, just taking the average of the minimums and the average of the maximums, I got a confidence interval of 34.5 to 41. But using the point estimates and the z table, it's actually much smaller, 36.4 to 37.9. Which is kind of interesting because it means that for all of these large intervals that you gave, the spread in the point estimates is not very large. Like, they're only between 35 and 41. The margin of error based on the point estimates is only the 50% margin of error is like, what is this? 0.75, twice half of 1.5. And for the 90% confidence intervals, it's good. You see it is a bit larger. I took this to mean that there's a bit of a deficiency in your odds settings, in that the 90% confidence interval is really not much larger than the 50% confidence interval. Just taking the averages of these, there probably should be more difference between them. And when we do it using the point estimates, this goes, so the range here is 1.5, the range here is 3.5. So the 95% confidence, or the 90% confidence interval is more than twice as big as the 50% confidence interval. And the answer, I'm 41 years old. I am. So, so thank you. And I am curious to, I hope there were, now that you've been in class, I'm not going to be able to use any responses that come after now, but any that came in up till now, I'm going to use for a 2-sample test to see whether I'm aging or not. All right. And I think it's time for you all to get down to lab. Thank you.